One of the most important steps in designing fluid lines, exhaust system, or any fluid transport system is understanding how the fluid actually flows inside the pipe. That's why computational fluid dynamics is essential. It allows us to analyze flow behavior before building anything in the real life. Welcome to Aromatics. Before diving into our simulation, let's briefly introduce laminar and turbulent flow. In laminar flow, the fluid moves in smooth parallel layers with very little mixing. This usually occurs at low Reynolds numbers for high viscosity fluids, low velocity, or small pipe diameters. Turbulent flow is characterized by strong mixing, vortex, and random fluctuations in velocity and pressure, and it occurs at high Reynolds numbers. In this video, we will start with a 2D simulation of turbulent pipe flow. See you in the ANSYS workbench. Drag ANSYS Fluent, right-click on Geometry, and choose Design Modeler. Look at XY plane, zoom in till 1 meter to make it easy. Cylindrical body appears as rectangle from the side, so we'll work with rectangle. Drag it from the origin. Dimensions it will be 1.5 meter in length and 0.1 as radius. Remember, we are working on 1/2 of the pipe. To convert it to surface, choose Concept, Surface from a sketch. Now you can apply our sketch to it and generate. Click on our surface and change the material to be fluid. Now we can move for mesh. Double-click on mesh. Select Z-axis, choose edge selection. Insert mesh sizing, select top and lower lines. Channel type to be the number of division, set it to be 80. Insert mesh sizing, select the inlet, change type to be number of division, set it to be 30. Change behavior to be hard. Apply bias to get accurate result near to the pipe wall. Set bias factor to be 10. Repeat the same thing for the outlet but with reverse bias option. Bias factor 10 means it gradually increases the division up to 10 times of the smallest one. Finally, insert phase meshing to the whole domain and generate. As you can see, it's a very structured mesh and have a good behavior near to the pipe hole. Minimum our boundaries to be center line, wall, outlet, and inlet. And you can get out, press on update mesh, then go to setup. Double precision. If you have a GPU, apply it to P1. If not, apply server processor according to your PC. From general, change 2D space to be axis symmetric. As we are working on turbulent model, change it to be K epsilon with enhanced wall treatment. Let's add a fluid. From Fluent database, choose water, copy and close. From cell zone condition, change fluid from air to your selected fluid. Apply and close. Boundary condition, the center line will be axis. Inlet, it will be velocity inlet with velocity of 0.25 meter per second. Change turbulence to be instancy with hydraulic diameter. Hydraulic diameter, it will be 0.2. Repeat this step for the outlet. From reference value, compute it from inlet, and reference unit will be surface body. From method, choose simple and change all the variables to be second order. From monitors, change residual to be 10 power negative 6. Finally, initialized, standard, and compute from inlet. After initialization, let's move on for calculations. Set number of iterations to be 500. Actually, it will end before this value. And finally, here is our residual. If you want to see the plot of velocity near to the wall and center line, from plot, choose XY plot. Y-axis, set it to be velocity. Choose wall and plot. As we can see, it's 0. And now let's see the center line velocity. Now we need to save our project and let's go for the post-processing to the result. Select contour, location it will be periodic one shadow, variable to be velocity, and apply. We can make it more clear by changing it to be 100. As you can see, here is the behavior or turbulent flow in the pipe. Now we need to see the full pipe. Duplicate the contour, go for view, apply reflection for ZX plane, let's make the same thing with the streamlines. Start with inlet, duplicate to make reflection, there is something interesting there. We can make a small video with the streamlines. So choose animation, the clip item, select our streamlines, make it slow. From option you can change some settings. There is another important thing, it's y plus value. Let's make a line with the same coordinates of pipe wall. From location, choose line. The name should be different from the name selection on mesh. Point 1 it will be 0, 0.1, 0, point 2, 1.5, 0.1, 0. And the sample it will be 100 and apply. Now choose chart. X variable it will be X. Location to be the pipe hole. Y variable it will be Y plus value. The Y plus values tell us how fine the mesh is near to the wall and whether it matches the chosen turbulence model or not. Each turbulence model has a recommended Y plus range. For K-epsilon model with enhanced wall treatment, accurate results are usually obtained when Y plus values is between 1 to 5. In our case, the Y plus value are above this range. So the mesh near to the wall can be improved by reducing the first cell height or adding more inflation layers along the pipe walls. That's all for today's video. See you in the next part with aeromatics.